All right, this is the 11.3 notes on geometric sequences. My first try at a video here, so be patient with me. It's probably going to be pretty bad. I know the audio is not very good either, but we'll see what happens. All right, geometric sequence. Only difference between a geometric sequence and an arithmetic sequence, which we already covered, arithmetic, is it has a common ratio. Now this is all fancy stuff, but it pretty much means that now to get from one term to the next term, you're going to be multiplying by the same number each time instead of adding something each time. So an example of a geometric sequence would be like, we'll start with 3, and then we have 6, and then we have 12, and then we have 24. And what would r be in this case, or what are you doing to get from one term to the next term? You're multiplying by 2. So if you're multiplying by 2, that would be the common ratio. We're multiplying by 2 between every term to get to the next term. That's pretty much what this says as well. It's fanciness for saying to find r, you can just divide any two consecutive terms. A sub n plus 1 divided by a sub n is a fancy way of dividing two consecutive terms. So if you took 24 divided by 12, you would get 2. 12 divided by 6 would be 2. You'd get 2 no matter what, and that's your r value. So we just found 2 is r. If you remember, for arithmetic sequences, we use d for the common difference between each term. For geometric sequences, we use r for the common ratio. All right, just like arithmetic sequences, there are formulas to find any term. To find the nth term of a geometric sequence, you take the first term and multiply that by r, which is the common ratio, n minus 1 times. Now, if you remember, for an arithmetic sequence, it was very similar to that. Like, you can either just memorize that formula, but for an arithmetic sequence, remember, it was a sub n equals a1 plus n minus 1 times d, because we were adding d n minus 1 times. So we were trying to come up with a way to memorize that we would just take the first term and add d n minus 1 times. Same thing here. To find the nth term of a geometric sequence, you take the first term and multiply by r n minus 1 times. So they're very similar to each other, but you need to have those memorized for the test. All right, now if we move down, for the sum of the first n terms, also a formula for it. So for an arithmetic sequence, we had a formula for that one as well. This one I don't have a great way to prove it to you right now, or a short way to prove it to you, so we'll just have to accept that is how to find the sum of the first n terms. So if we want to add up a bunch of them, we'd use that formula. And then this is the sum of an infinite geometric sequence, which gets a little crazy, but now if I just keep adding the terms forever, you would think, well, they can't stop ever, but they will as long as r is between -1 and 1. In other words, if it's some fraction between -1 and 1, the numbers are constantly getting smaller. So if they're constantly getting smaller, it will approach some number. And we'll use this formula as well for an infinite. So we have 3 formulas here, and pretty much all we're going to do today is apply those 3 formulas. So let's go look at some of these examples. First one, determine if the following sequences are arithmetic or geometric. So let's start with that. Let's just do this first sentence here, determine if these are arithmetic or geometric. So the first one, well, to get from 2 to 4, I could either be adding 2 or multiplying by 2, so I'm not sure yet. So I go to the next one, but to get from 4 to 6, I realize that I'm adding 2. So this is arithmetic. And I can't write on here at all, so let's A-R-I-T-H for arithmetic. Sounds good. Because we're adding something each time. And this one over here, if you notice, to get from 3 to 6, you can either add 3 or multiply by 2. But then to get from 6 to 12, you see that you're multiplying by 2, and then 12 to 24. So this one is geometric because we are multiplying by the same number each time. And that's just geom. What's going on here? To get from 6 to 2, I could either be subtracting 4, but I notice that that's definitely not the case from there on out. So to get from 6 to 2, I divided by 3. To get from 2 to 2/3, I divided by 3. So you're like, hey, I think it's dividing by 3. But geometric terms, you have to multiply by something. So this is geometric, but you're not dividing by 3. You're multiplying by 1/3. So this is geometric with r equaling 1/3. Because if you keep multiplying by 1/3, that's equivalent to dividing by 3. This one we should have wrote it over here. It has an r value equal to, I don't know what that circle's doing, sorry. An r value equal to 2. And this had a d value that was equal to 2. So notice the difference between arithmetic and geometric sequences. Arithmetic, you're adding the same number each time. Geometric, you're multiplying. So no big deal, but now we have different formulas for each one. So the next question, or next part of this question says find the nth term. To find the nth term, we have a formula for arithmetic. an, or the nth term, is always the first term, a sub 1, plus n minus 1 times d. So if that's the formula, and we have it memorized for the test, all we have to do is apply that formula. To find the nth term of this sequence, we would just put a sub 1, which is the first term, is 2, plus n minus 1 times d, and d is also 2. And then we could distribute this 2 in here to clean this up a little bit. So we just do a little bit of algebra here. We get 2 plus 2n, that's a minus sign there, 2n minus 2. Clean that up some more. Let's see if I can bring this down, sorry. And the 2 and the minus 2 cancel each other out, so we just get 2n. And that will give you the nth term. So if we finish this off, it says also find the 7th term. Well, now that I have a formula for any term, if I want to find the 7th term, I just do, all right, well, a sub 7, which is a fancy way of saying the 7th term, and I just plug 7 in for n. So 2 times 7. So the 7th term is 14. It also says find the sum of the first 7 terms of each sequence. So to find the sum of the first 7 terms, there's a formula. The sum of the first n terms, first let's see if we remember the formula for arithmetic. This is arithmetic. So we're going to show these next to each other. Is a1, so it's a good review for you, plus an, which is the last term, all divided by 2, and that value, or that quantity I should say, times n. And we talked about this, try to memorize this as being the average of the terms times how many terms. Well, in this case, if we're trying to find the sum of the first 7 terms, we would say the sum of the first 7 terms is a1, which is 2, plus a sub 7. Notice n here matches this n, so if I'm finding the sum of the first 7 terms, then I need to know the 7th term. Well, the 7th term we found up here, it was 14. All of that divided by 2, and then times how many terms, which in this case is 7. So n is indicating how many terms we're trying to add up. If we add that up, 16 divided by 2 is 8. 8 times 7 is 56. So the sum of the first 7 terms is 56. Now that's review. That is all the arithmetic stuff that we should already know how to do. We're guaranteed to have to be able to show you, or you have to be able to show me that you can do that on a test. Now geometric, the same thing. How do we find the nth term? Well, the nth term, there's a formula again. It's right up above here, and I'll just write it down again. It's the first term times r, n minus 1 times. N minus 1. So if you want to take a1 times r to the n, so the formula would be the first term here is 3. So a sub 1 is the first term. The first term is 3. Having some problems here with my equal sign. R is 2, so times 2 to the n minus 1 power. Now you can't multiply these together. You can't say 6 to the n minus 1 power because that 2 needs to be raised to this power before it can be multiplied by that 3. And I can't take 2 and raise it to the n minus 1 power. So that's as cleaned up as it gets. So that's the nth term. But the directions say also find the 7th term. All right, so if we want to find the 7th term of the sequence, we say 3 times 2 to the 7 minus 1 power, which is really 3 times 2 to the 6th power. And 3 times 2 to the 6th power is 192. So the 7th term is 192. Now we could also have generated that here by just continuing to go. And I know some of you want to do this all the time, but if I asked for the 100th term, this would take a while. Like if I went 48 to 96 to 192, and that would be the 7th term if we count 1, 2, 3, 4, 5, 6, 7. So we could have generated it by just continuing to generate the sequence, or we can use the formula. The formula is nice when you get to large values of n. All right, we also need to find the sum of the first 7 terms. So for the sum of the first 7 terms, we have another formula up here. So if we go up here and look at this formula, it's a1. It's this guy right here is the sum one. a1, 1 minus r to the n over 1 minus r. So I'm just going to put that down here again so we have it ready to go. This one's a little bit more complicated, but you can memorize this. 1 minus r to the n over 1 minus r. That's an r there, and that's a minus there. All right, so let's see if we can just plug and chug in this formula. The 7th, to find the sum of the, this is the sum of the first n terms, sorry. So to find the sum of the first 7 terms now, we still do a1, which was 3, which is the first term, over 1 minus r. R was 2. We're trying to find the sum of the first 7 terms, so we put a 7 there, all over 1 minus 2. And this is a plug and chug. Make sure you know how to use your calculator to do this. So this is a good exercise for you to try right now, is actually type that in your calculator. Can I take 3 times this? Now, you Inspire people can type this in as one big massive fraction, which is nice. If you have an 84, you have to be very careful with the parentheses. I would suggest to do this first on an 84 and then take my answer times 3. But no matter what you do, you need to know how to come up with a correct answer to that or plug it in correctly, which ends up being 381. And again, if we wanted to check that answer, if we added up the first 7 terms, so if we just added all 7 of those terms right there, we should end up with 381. So just to make sure you understand what you're doing. All right, we can do the same thing over here with this one. To save some time right now, I'm not going to do that, but we could do the nth term. We go through and do all this stuff, exactly the same thing with part C there. All right, example 2 says, find the sum of the infinite number of terms. All right, an infinite number of terms means keep adding up forever. It does not make sense that it will ever add up to something if it's an infinite number. However, it only works if it's geometric and if r is between -1 and 1. Well, if you look at part C, r is 1/3. And notice these numbers are continuing to get smaller. The next number here would be, if we're multiplying by 1/3, would be 2/27. So that's really small. And the next number would be 2 over, and 27 times 3 is 81. So 2 over 81. I mean, they're continuing to get very, very small. If I kept adding these forever, eventually it'd be like adding 0 at the end. We'll never add 0. We'll be adding such a small number each time that it'll be very insignificant. So this does have a sum that it's approaching. And that's a little more calculus and limits, but the formula for the infinite sum is right here. So that's what we have to have memorized for the test. It's a1 over 1 minus r. So if we come do that one down here, the sum of the infinite number of terms is a1. And what was a1 in this case? A1 was 6. A1 just meaning the first term. So the first term was 6. So we're going to take 6 divided by 1 minus r, and r was 1/3. That's a terrible 1/3. So we end up with 6 over 2/3. And dividing by 2/3 is the same thing as multiplying by 3/2. So 6 times 3/2, which ends up being 18 over 2, which is 9. So if you kept adding those numbers, and maybe this is something you want to do on a Friday night when you have nothing better to do, is just keep adding these numbers up. Keep going forever. Multiply by 1/3 and add it, multiply 1/3 and add it, one time multiply by 1/3 and add it. You'll find out that if you keep going for a very, very, very long time, that it will never get over 9, but it'll get closer and closer and closer and closer and closer to the number 9. So that's why that sum of that infinite series is considered to be 9. I think that's a pretty cool formula, and we'll do some applications of that later on. But you got to memorize that one. There are 3 formulas today. It's pretty much just using them. We have to memorize these 3 formulas. The nth term, the sum of the first n terms, and the sum of the infinite number of terms of a geometric sequence. Infinite terms here, when we're adding them up, is really called a series, which is kind of cool too. All right, now let's see if we can be in the woods and apply this situation. Find r. All right, you're on an ACT test, and it says, what's r of the following geometric sequence? You're like, I have no idea. Well, if you have no idea, you start generating the terms. N is what term it is. So if I want to find the first term, I would just plug 1 in there. If I plug 1 in there, I have 1/3 to the first power, which is 1/3 times 2. So the first number is 2/3. To find the second term, I would plug 2 in there for n. Well, orders of operations say we need to take 1/3 and square it first, which is 1/9. And then 1/9 times 2 would be 2/9. So the next term is 2/9. Now, since it said it was a geometric sequence, I should be able to find r right now by just dividing any 2 consecutive terms. But let's find one more just to see if we can really find it without actually dividing those terms. So the third term would be 1/3 to the third power, which is 1/27, times 2, which is 2/27. So there's the third term. Well, I can definitely see now that to get from this term to this term and from this term to this term, I'm multiplying by 1/3. So I realize that r is equal to 1/3 by generating that sequence. And you can do that on any type of problem like this if you ever get stuck. Now, there is a way to memorize this, that if it's written in this form, if the sequence definition is in this form, whatever is being raised to the power is r. So that is r right there of 1/3. This one over here, the same thing would be true. I'm going to let you go ahead and do that one on your own if you want, but you just start plugging in the terms. Plugging in 1 for n. Well, maybe I should do this one. To plug the first term in for n, or to find the first term, we plug 1 in for n. On the top, 2 to the first is 2. Here we have to do the power first. 1 minus 1 is 0, and then 3 to the 0 power. Everybody in unison. There's nobody here, so yeah, I'm talking to myself, but 3 to the 0 power, or anything to the 0 power, is 1. So I end up with 2 over 1, so the first term is 2. To find the second term, I plug 2 in there, I plug 2 in there. 2 to the second power is 4. 2 minus 1 is 1. 3 to the first is 3. 4 over 3 is 4/3. So what am I multiplying by to get from 2 to 4/3? And pretend I'm Dora right now, blinking my eyes, and I'm asking you, what can we use in our backpack to solve this? But what do you have to do to get from 2 to 4/3? Right. You have to multiply by 2/3. And if you take 2 times 2/3, you will get 4/3, so we just found r by generating the sequence. All right, let's go to the next page. Go to the back side of this thing. I don't know how to do this really well, so bear with me. All the way up to the top. All right, find the sum. Oh, my favorite. All right, we have a sum formula. Pretty easy sum formula. We got to just use that sum formula. The problem is we need to know how many terms there are. So the only question is, because it's telling me to stop at this term, is what term is this? Is this the third term? Well, here's the first term. Here's the second term. Here's the third term. Then this dot, dot, dot means a whole bunch of other terms. Then we get to this one. Now, it's very misleading. You're like, I see a 15, so I think that's the 15th term. But notice the third term had squared as a power. The second term, and there really is a 1 right here, had first as a power. And the first term must have had 0 as a power. So therefore, this number is not what term it is. It's actually, the term is 1 bigger than that power. And we just get that from problem solving by looking at the pattern. This must be the 16th term. So therefore, we're finding the sum of the first 16 terms of this sequence. Using the formula from the other side, it says take the first term, which is 1/5, and multiply it by 1 minus r. Oops, what's r? What are we multiplying by each time to get from this term to this term and this term to this term? In this case, again, if you can just, how do I get from 1/5 to 3/5 if it's geometric? Is I'm multiplying by 3. So r in this case is just 3. If r is 3, then we're going to do 1 minus 3. If you remember the formula, it says to the nth power, which in this case would be the 16th power, all over 1 minus r. Again, just using the formula. It says a1 times the quantity 1 minus r to the nth over 1 minus r. Again, knowing how to plug that into your calculator is vital, so make sure that you do know how to do that. To check that answer, if you want to do it right now and pause this to see if you know how to do it, it's 4,304,672 should be your final answer. All right, this one. And if you need to pause or ask, put a star next to this to say, you know what, I need to ask how to use my calculator, because if you type this in and don't get that answer, then you just don't know how to use your weapon of math instruction. So we'll have to get to that. All right, this one looks the same, except for it says dot, 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 and doesn't end. If you see something like this, this is infinite. And the only way an infinite series, or an infinite geometric series, this is bad. I'm having some problems here. So the infinite is the dot, dot, dot stuff. It goes forever. Is if r is between -1 and 1. Now, one thing you notice here is that the terms are alternating from positive to negative to positive to negative. You're like, what's going on with that? But we're really adding. We're not adding then subtracting, adding then subtracting. We're always adding. We're just adding positive and negative numbers. If that's true, r must be negative. If r is negative, the terms will alternate from positive to negative. So how did I get from 1 to 3/4? If I multiplied by something, I'm also multiplied by -3/4. And then to get from -3/4 to positive 9/16, I must have multiplied by -3/4 again. And look, it works again. If I multiply by -3/4 again, I'll end up with 27, or -27 over 64. So I know that r is -3/4, because that is the number that I'm multiplying by each time And again, R will be negative if the terms alternate from positive and negative. So R is negative 3/4. If R is negative 3/4, that is a number between -1 and 1. Therefore, it will have an infinite summation. So let's try to find it. The formula, the sum of an infinite series, geometric series, is A1, which in this case is 1, over 1 minus R, which in this case is 3/4. And that's it. It's A1 over 1 minus R if you look on the other side there. So 1 minus 3/4 is 1/4. Or excuse me, 1 minus negative 3/4. I was going to say that's not right. R is negative 3/4. And I just made the mistake that I don't want you to make. If R is negative, then we do minus a negative. Minus a negative, we should know, is plus a positive. So it ends up being 7/4 down there. And 1 divided by 7/4 is really 4/7, which seemed kind of odd, but that is the sum. If you kept adding those positive and negative numbers and positive and negative numbers and positive and negative numbers, you get closer and closer to 4/7. So that's how you do an infinite, which we've done before. Oh, but now the fun begins. Words. We love words. We want to apply math in every situation all the time. The ball is dropped from 10 feet and bounces up halfway each time. How high is the ball after 3 bounces? All right, I'm going to start with just a diagram of what's going on here. Now, the ball is really just coming straight up and straight down, but to try to help, I'm going to put it out on an angle as it going up and straight down, but it really is going straight up and straight down, but it's kind of hard to see. So here's the ball. It starts out 10 feet in the air, and we bounce it. Now, it would be straight down, but I'm just going to kind of go on an angle so you can see this. It bounces and comes up halfway. So that means here, it was at 10 feet, and here, it's now at 5 feet. Now, every time it bounces up halfway, this magical bouncy ball, so it hits again, and now it comes up halfway to 2.5 feet. And then it bounces and comes up halfway to 1.25. So we just start generating this. We're like, oh, look at this. This is a sequence. There's a pattern here. It's always coming up half as much. What kind of sequence is it? Is it arithmetic or geometric? Well, if we're going from 10 to 5 to 2.5 to 1.25, we're multiplying by 1/2 each time. So it's geometric. Well, it says how high after 3 bounces. So I want to make sure we understand that this was how high it was after the first bounce. Like this 10, it hadn't been bounced yet. So this was really the first term. That's after 1 bounce. This is after 2 bounces. This is after 3 bounces. So how high is the ball after 3 bounces? 1.25 feet is the correct answer. No fancy formula needed. Just kind of figure out the problem by reading the words and figuring out, oh, how high after n bounces? Now we do need it because we're just doing in general. N just means in general, what's the formula to calculate it? Well, this is not a formula, but I did start to generate the sequence. And I have memorized we have to know it's geometric. A geometric sequence, the nth term, is always equal to the first term. And what's the first term in this sequence? We said, 10, it hadn't bounced yet. So after 1 bounce, the first term is 5. So 5 is the first term, times, and then it says, that's a multiplication, times r, and we said r was 1/2, because that's what we're multiplying by each time to get from this term to this term to this term. R is equal to 1/2, and maybe I'll write that over here. This is geometric with r equaling 1/2. And notice it never says that in the problem. You're going to have to be able to distinguish that on the day of the test. And then to the n-1 power. The formula just says a1 times r to the n-1 power, which, there we go. That's how high it is after n bounces. So if I wanted to find out how high it was after 3 bounces, I could plug 3 in for n right there. And if we just kind of quickly do that in our head, 3 minus 1 is 2. 1/2 squared is 1/4. 5 times 1/4 is 5/4, and 5/4 is equivalent to 1.25 feet. It all works out. It's amazing. All right, how high after 8 bounces? Should be pretty easy now that we have a formula. We just plug 8. Oops. So we're now finding a sub 8, or we're finding the 8th term of the sequence. So 5 times 1/2 to the 8 minus 1 power, which is the 7th power. Make sure to inspire people that you're putting either all of this in parentheses, so make sure it takes the whole thing to that power, or inspire people to, or you're putting that in parentheses, but you got to make sure you're doing it right on your calculator. You got to know how to use your calculator to get the correct answer. If I raise that to the 7th power, I end up with 5 over 128. But that's going to be tough. So you can also put it in decimal form if you want, which is 0.039 feet. So make sure you know how to use your calculator again. Get practice with that. What is the total distance the ball will travel before it stops bouncing? Part C. Well, according to this, the ball will never stop bouncing. Now, it's like theoretical versus actual because it keeps bouncing up halfway. So it's always going to keep bouncing halfway, but eventually, way out here, it's not really going to be moving at all. It's going to be moving up and down so little. So if it says forever until it stops bouncing, it really doesn't stop bouncing. So this is code for an infinite series. So this is the sum of an infinite series. Now this only works if r is somewhere between -1 and 1. But remember, in our case, r is equal to 1/2. So this should eventually reach some limit somewhere. So we can use the formula, which says take the first term, which we said was 5, over 1 minus r. R is 1/2. 5 over 1 minus 1/2 ends up being 10. Now, if you circle that answer, at least you understood, that's what it seems to be approaching. But I love this question because it says, what is the total distance the ball will travel? If you would look at 10, 10 is just, if I add up all these numbers, the 5, the 2.5, the 1.25, and if I kept adding those numbers, I would get to 10. But notice, every time it comes up to a height of 5, it must have traveled up 5. Whoa, I don't know what I just did there. In a different color here so we can see this. It must have traveled up 5 and then back down 5. And remember, this is going straight up and down. I'm just putting it at an angle so we can see it. So really, for every time that it went up 5, it also went down 5. And when it went up 2.5, it went down 2.5. So if we added up all of these numbers to get 10, we really need to double that to find out the total distance traveled, up and down, up and down, up and down. So a little problem solving skills here, which is awesome, or I think is the most important thing. This is not the total distance traveled. That's just like all the ups, let's say. And we forgot to calculate all the downs. So we need to multiply that by 2. So we got, all the downs are twice as much. So now we're up to 20. Well, we're still not going to get the answer right because the original ball started up here 10 feet in the air. We started at 10 feet and it fell the first time. I don't know what's going on there. It fell first time 10 feet. Now it didn't go up 10 and down 10. It just went down 10. So if it just went down 10 on the first one, I need to make sure I add that distance in there because the ball traveled that 10 feet. And then it started going up 5, down 5, up 2.5, down 2.5. For that first fall of 10 feet, I never have in my calculation. So I need to add 10 to this. So my final answer is 30 feet, which is it's a fun problem to actually think. I don't want you to just turn into robots and just plug the numbers in. That actual thinking part is a lot of fun. So that's the total distance the ball will travel before it stops bouncing. It's an application of an infinite series of a geometric sequence. All right, that's the first video. Hope that helped out. You can do the homework and use this as a reference if you need it.